All right. Welcome, bio students, to basic chemistry. I'm starting off with a cartoon, maybe not the most amazing cartoon, but the name's Bond, hydrogen bond. Um, and this is actually a pretty good cartoon for where we want to get to because hydrogen bonds are going to end up being a super important part of what we're looking at in the class. So let's get rid of that. All right. This is set up. The scale of the universe is this activity. So if you haven't seen that video, I'd like you to go back and look at that. Remember, we're going to be looking at 1 times 10 to the negative 6 for the work that we're doing. But really, when we're looking at atoms, we're at 1 times 10 to the negative 10, probably 1 times 10 to the negative 9. So 6, 3, 4 more orders of magnitude down in terms of the size. So none of the things that I'm going to be talking about are visible to the eye because the wavelengths of light are too big to be affected by the things that we're talking about. So we're going to look here at elementary particles. These elementary particles define, so the first and most important elementary particle is the proton. This defines what an element is. So this makes an element what it is to be an element. I cannot stress this enough. So this is like you are you are you. This is who you are. You could have different feelings, you could have different behaviors, but you're always you. A proton is what makes an element an element. So if an element has 6 protons, it's a carbon by definition. Um, that's what it means to be a carbon, is to have 6 protons. The protons are located in the nucleus, positive charge, contain a significant mass. So hopefully that's all, maybe not exactly a review, but something that you've seen you can read in the textbook. Electrons. Electrons, I think one of the best ways to think about electrons is electrons affect the behavior of the element. So electrons are really gonna talk about how an element acts or interacts. They have a negative charge of 1, which that exactly matches the proton. They have basically an insignificant mass, and they are quite far from the nucleus. If you think about an atom consisting of a cloud of electrons and protons, what it means is that 99.9999% of the atom is empty space. That it's kind of like, in this way, it is like the solar system. The amount of matter in the solar system is very, very small compared to the amount of space in the solar system. So the same thing is going on with these elementary particles. And then finally, we have neutrons. Neutrons can vary in number. When you have a different number of neutrons, you get what's called an isotope. Um, we'll talk about that a little bit down a little bit further. But generally, they're close to the number of protons. They have no charge, but they have basically the same mass of proton. And again, no charge. How do you remember such a complex thing? You can think about this super hilarious cartoon or joke where the neutron walks into a bar and orders a drink. He asks, "How much does it cost?" And the bartender says, "For you, no charge, because you're a neutron, no charge." All right, so hopefully you'll take a second right now and you will fill out this chart here. So what I want you to do is write out the location, the charge, and the mass in AMU for each of these 3 subatomic particles, right? This is an atom. So a subatomic particle would be below or smaller than an atom. Proton, neutron, and electron. These are our three subatomic particles. Do. All right, so you will have done that. Location, because I can't write very well with this, I'm just going to write N for nucleus, N for nucleus, and O for orbiting. So that's where those three things are. Charge, 1 plus, neutron, 0 charge, and electron, 1 minus. Proton, 1 AMU, neutron, 1 AMU, and electron really is basically 0. So if you want to do little squiggly lines here, you can do that. So those are our charges for the parts of an atom. Then moving on. Atom. All right. This is a little kind of diagram that helps us think about the way things work. So what's the operational definition of an atom? What are the characteristics? Give an example and give a non-example. Again, I'm going to give you a little bit of time to think about this and fill this out. I'll probably ask an Edpuzzle question prior to that, prior to me writing on it. All right. So I think I'm going to say this. It's going to be too hard for me to write, I think. Maybe. Let's see if I can do this. No, there's no way I can write this. So sorry, y'all. You're just going to have to deal with me saying it. Operational definition. I would say this is the smallest particle with unique characteristics. I'll repeat that. An atom is going to be the smallest particle that has unique characteristics. Characteristics cannot be seen, interact with other atoms, will bond with different things. Those would be the characteristics that I would think. Examples: hydrogen, helium, oxygen, nitrogen, carbon, boron. Non-examples: H2O, CO2, proton, electron. So I did 2 molecules on top and then 2 subatomic particles below that. So those would be non-examples of an atom. I think we'll do one more here and then I will save the rest for our next slideshow. All right, here we go. Periodic table. So several super clever people determined how it is that atoms can be organized. And they were organized, again, you can't see these things, so they're organized by their behavior. And when they put all this together, they realized that atom behavior follows a particular trend. And that trend can be shown by placing atoms in a particular order. And then this gives atoms all of their characteristics. So first of all, let's talk about the language of the periodic table. These are columns that go up and down. These are also called groups. And then rows go across, and rows are called periods. But I'll call them columns and rows. I might call them periods and groups as well. But generally, it doesn't matter to me that you understand that. When you're reading the periodic table, just like when you're reading a book, you want to start on the upper left-hand side and move across the period or the row. So even though there's a big gap there, you go from H to He, from hydrogen to helium. Then you do a return, and you go back here to lithium, so Li. And then you go all the way across again, return all the way across. Now this is a big and kind of a complex picture, but the good news is really, the stuff that you have to know seriously is right here. That's the part that I want you to have a good sense of. We'll be doing a little bit here, a little bit with potassium, chlorine, sulfur. Some of these we'll be using as well. But we're going to be focusing just mostly on the top. And you don't have to memorize any of this, but you do have to understand it. So that's essential. And we'll get to why you have these gaps here, particularly just this gap, and it's the same thing with the D block and F block of transition metals. Let's go one more and see. All right. Yeah, and then what I want you to see here is, I like this image a little bit better. This is the atomic number. Hopefully you will remember the atomic number is the number of protons. So hydrogen has 1 proton. If I gave another proton to this atom would become a new element. It would become helium because it's the number of protons. I could give it another electron, it wouldn't change it. I could give it another neutron, it wouldn't change it. But if I give it another proton, it changes its essence. Protons determine the essence, okay? So hydrogen has 1 proton, helium has 2 protons. We go all the way back down to lithium, 3, beryllium, 4, 5, 6, 7, 8, 9, 10, until we get to neon, and then we go back. The reason we do these carriage returns, or these returns from helium on the right-hand side over to lithium on the left, is because the behavior of the element changes as we move, as we move on. And so we'll talk about that more in the next set of presentations. But I think this is where we will end for this presentation.